Yeah, we will see what is MD-range policy, how it is used in typical Kokkos code, and then we will look at recent updates from the CEA team at CEA France about improving MD-range policy performance. And then we will look further at two topics regarding auto-vectorization in the context of multi-core CPUs and about how to use loop unrolling to improve performance. Along the way, we will discuss some broader themes like how to borrow ideas from the performance optimization community and how to give more control to the user by trading some productivity but getting a better portable performance by doing that, and how we can keep expanding our benchmark suite so that we can test our ideas and improve performance. So what is MD-range policy? So we know that views are the most fundamental data structure for Kokkos. And in order to run parallel computation on views, we need execution policies, and MD-range policy is one such execution policy. And it can run for either a parallel 4 or a parallel reduce over an n-dimensional range, high dimensional space up to 6 dimensions. And it does it in a tiled manner. That's something that you have to keep in mind. It divides the high dimensional grid into tiles and iterates over those tiles. Now, when it comes to parallel 4 and MD-range policy, a few things we have to keep in mind. Parallel 4 as such assumes that the iterations are independent of each other. And this readily maps to various scientific computing kernels like stencil computation and so on. And in the case of MD-range policy, you're not going to get the ability to use a scratch space inside a parallel 4. In case you want to do that, yeah, you have to look elsewhere. You have to look into hierarchical parallelism. And we have ways to do it, multidimensional iteration in hierarchical parallelism. So what is this MD-range policy class? So in order to create an instance of an MD-range policy execution, you have to keep a few parameters in mind. Let's look at a few of them. So there is this notion of rank, which defines the size of the number of dimensions in the iteration space. And it also comes along with these iteration orders, which can be set by default by Kokkos for you in a suitable manner. And that is because we need this notion of how to iterate over the tiles within the grid and also how to iterate within the tile. And another thing that you have to keep in mind is there is also this notion of layout when it comes to views. So again, layouts can be set suitably by Kokkos for you by default. But the iteration order of MD-range policy and the layout of the views with which it works with, they have to match to give good performance. And we have a few other arguments to keep in mind, say how to specify the range over which the computation happens, and also the tile dimensions. That's something that can be tuned, and it is optional. Again, Kokkos can set good default sizes for you, tile sizes for you, and we will see how it has been improved recently by Adria. So we will see about how to use MD-range policy with parallel 4, and you can see that Kokkos up there, you need not specify the iteration order. It can do it for you in a suitable manner according to the backend. For example, for multi-core CPU, iterate right is a good way to iterate through the iteration space, and Kokkos will do it for you. And as I already mentioned, Kokkos can set the layout also by default for views. And if you see this usage example, one thing that you have to keep in mind is how you define the lambda. So the number of indices should match the rank of the MD-range policy. So whatever computation happens inside, it's with respect to these indices that you call the lambda with. So let's look at some recent improvements for improving MD-range policy performance that came out of the CEA team. So to start with, to do any kind of performance improvement, you need good benchmarks to test your ideas on. So we made 2 PRs regarding stencil kernels and also the stream benchmark kernels made by Travis and Adrian. So you can see further about them in the PR description mentioned here. And this is just a starting point. This can be extended further and further. For example, we can improve the kind of stencils that we test with. We can increase the radii of the stencils. We can increase the degrees of freedom at each point in the domain, and we can play around with the kind of computation that happens, so that we move towards more compute-bound kernels. So typically, these kernels are pretty memory-bound, especially the stream kernels. Now, when it comes to doing some performance improvement using these benchmarks, so there has been some recent improvement by Adrian for the GPU backend. So just some background on how MDRangePolicy executes on GPUs. So we saw this notion of tiles. So these tiles map to thread blocks of GPUs. And when it comes to GPU execution, yeah, we have grids of maximum dimension 3. So we have to see how to accommodate n-dimensional ranges up to 6 and execute them on the GPU. So that's where this class called device iterate comes into the picture. It's an internal detail in Kokkos, which does this mapping from the high dimensional space, n-dimensional space to does the mapping from the block and thread indices of the GPU to the indices in the high dimensional space rather. And using these indices, it can call the user-defined functor. So, so Adrian had a look at how this device iterate class is implemented, and he has streamlined its implementation, and due to which, first of all, it executes in a more efficient manner, and also it takes care of certain resource utilization. It has reduced the resource utilization. So it overall leads to performance improvements. Say, for example, you can see that with the copy and add kernels of the stream benchmark. And also, along through this PR, he has fixed one issue that we have been facing with Kokkos, wherein some users, when they tried iterate right iteration order with layout right views, they were not getting good enough performance. It was pretty bad. Yeah, it is true that layout left with iterate left is what is suitable for GPUs, but at least for certain kind of computations, with iterate right, with layout right, should perform well. Say, for example, for these memory-bound kernels like the stream kernels. So this issue has also been fixed along the way, and that is one of the reasons is due to this recursive template-based implementation that he has made. And further, he has improved the default tile sizes that are going to be proposed by Kokkos for the GPU backend. So here you can see what has been done for CUDA and HIP. He has done similar modifications for SQL also. And this also leads to improvement. So the plots that you see here show the performance on top of the green bars that you see, are the performance improvements that you can see on top of the refactoring that he has done to the device iterate class. So you can see that the refactored device iterate class along with this newly proposed default tile sizes do lead to improvement. So let's do a small detour. So one broad theme that you can keep in mind while you are trying to improve performance for MDRangePolicy is this topic of loop nest optimization that has been widely studied in the compiler optimization community. So when we talk about tiles and about tile sizes and so on, all those ideas are coming from the loop nest optimization literature in performance optimization community. So compilers continue to get better at these, but at the same time, people who develop the backends like Kokkos also try to bring in their ideas to make the backends better, to make it more suitable for compiler optimizations. And also having a better understanding of these ideas helps in developing good tools, like for example, Apex, which can help in runtime tuning of tile size in Kokkos already. So that's something that we can already try. So we will see two more themes from this loop nest optimization community based on auto vectorization and loop unrolling. So typically, when some user faces issue with MDRangePolicy, they'll post an issue about it. And for example, that's how that iterate right issue came up. Similarly, there was this issue which came up in which there is this user who was trying to compute 3 stencils at the same time, So you can see that it's a two-dimensional stencil. There are 3 such stencils, totally involving 10 views. So there is a lot of memory traffic involved. So you can do the computation in 2 different ways for any given stencil. Either you can have an explicit for loop inside a range policy, such that you take care of both the indices into the two-dimensional views, or the more intuitive approach is the MDRangePolicy based approach, wherein you just have the stencil computation happening inside the lambda. Yeah, unfortunately, the range policy based implementation with 3 separate parallel for calls performs best, and the MDRangePolicy based implementation with 3 separate parallel for calls performs much worse. So at the same time, this MDRangePolicy based implementation works acceptably well for the multi-core setting for the same CPUs. So yeah, now comes the question of portable performance. The user wants to have the same code which will run for both in serial and multi-core setting. So you can refer to this issue for further details. So if you see, in the serial backend, again, the MDRangePolicy is going to iterate over all the tiles, but in a serial manner, one after the other. Even though there is supposed to be some reuse in the tiles, apparently it's not helping enough. So what happens if you see in the parallel for case? Yeah, parallel for will be calling the user-defined functor inside a for loop. And in our case, our user-defined functor has an explicit for loop. So when it gets inlined here, we are going to essentially get a nested for loop. And so one idea that we can possibly try is to have an implementation of MDRangePolicy, which will be based on a nested for loop to mimic what anyway that range policy is doing with an explicit for loop, and see whether that leads to performance. So yeah, it does lead to some performance, but still it's quite far away from what you can really get with range policy with an explicit for loop inside. So that makes us wonder what is going on. So what is happening is there is auto vectorization that is happening with the explicit for loop that is inside the range policy. So unfortunately in MDRangePolicy, that even when you do that nested for loop based implementation, auto vectorization is not happening by the compiler. And probably one of the reasons could be that there is a little more indirection that is going on with the nested for loop implementation of MDRangePolicy. And one more thing to keep in mind is our current implementation of MDRangePolicy also tries to auto-vectorize the iterations that happen over the tiles. So there also no auto-vectorization happen. So probably a better implementation of the MDRangePolicy for based on nested for loop is possible. I can discuss with my colleagues in the Kokkos team and see whether that can be improved. And one other possibility is to come up with a custom compiler optimization. Yeah, it is a little not so portable for sure, but at the same time, it will be a nice exercise because we are so close as far as parallel for is concerned, because all the semantics of parallel for says that all the iterations are independent of each other, and whatever views are going to be used inside the computation in the user-defined functor, they are not going to do anything crazy. So in terms of aliasing, so we are quite far, but at the same time, yeah, this is not so portable in terms of a solution. So there are a few further complications. For example, if there is going to be conditional control flow inside the user-defined functor, yeah, that is a challenge to parallelize using SIMD operations. And also, when there are going to be complex loads and stores, there was an excellent talk by Nigel Tran yesterday about this topic. So generating vectorized code of the user-defined function is not so easy, but at the same time, there are many straightforward cases which can be vectorized, I feel, and it could be a good project, probably for a master's student. Yeah. And there is considerable existing work that is there from the loopness optimization community in compiler literature. There is considerable existing work already, which can help. So again, a small detour. We see that there is this performance, portability, and productivity trade-off that we always have in mind. But it will be a good idea to sacrifice a little bit of productivity in order to achieve more portable performance. Yeah, we can do this first by developing better benchmark suits that we already discussed about. And also we have to improve and expose more knobs to the user, both at compile time and runtime. And of course, we have to keep improving tools like Apex to give better control for the user to improve performance. So we will see how that could possibly be done using the topic of loop unrolling. So if you see, there is this PR which happened a few months ago, which introduced unrolling for grid stride loops for range policy for the CUDA backend. And it will be good to explore the same kind of unrolling in the context of unrolling individual dimensions in the nested for loop. So in general, we know that how loop unrolling can be useful in so many ways since it's going to improve with instruction level parallelism, and also it can reduce the number of loads and stores, and of course it's going to improve SIMD code generation. But there are things that you have to keep in mind also about resource utilization. Now, as one small comment about loop tiling and loop unrolling, let's just focus on the last 2 points. So tiling is something that can be tuned at runtime, but and already Apex lets us do that. But unrolling is something that involves code generation, and it has to be done at compile time or in a just-in-time manner. Now, again, compilers have got pretty good at doing unrolling. For example, GCC with aggressive optimization level is going to try unrolling as one of its big tools for achieving better performance. And also the loop trip count need not be known at compile time for for doing the unrolling. But still, there can be many situations where the compiler does not do what the user wants for that particular application. So that's where guiding the unrolling by the user can be quite helpful. So especially if we can do this in a per loop basis to start with, say for example by using pragmas. So we all know how there are pragmas for loop unrolling, and it can help the user write code which is still quite easy to read, and it can help systems like Kokkos to come up with abstractions which can be portable across different backends. Because pretty much all the backends have pragmas for unrolling, and so it will be nice for Kokkos to have macros in like the following. And there are such macros already in other systems like Raja, Mojo, and Cutlass. And we could give users such macros which they can use inside parallel constructs and also in host and device functions. And when it comes to MDRangePolicy, yeah, such macros will be used internally. So we will see one small example wherein unrolling along a particular dimension could help with MDRangePolicy. Okay, this is just some simple CUDA code, but this can readily map to an internal implementation of MDRange, wherein all the logic that you see on the left involving X, Y, Z, 0, Z, basically those are the computations that happen in that class, the device iterate, to compute the indices to index into the user functor. And what you see on the left is pretty much the user-defined functor that is passed to the parallel for. So you do see that there is performance improvement with a suitably chosen unroll factor, and this unroll factor is along the Z direction in this case for a 3-dimensional problem, a stencil computation. So looking at a plot like this leads us to the natural question, okay, how to choose this unroll factor? So yes, there are heuristics, machine learning based techniques and so on to do this, and also there are iterative compilation approaches to choose this unroll factor. And again, that is an opportunity for performance optimization tools in the Kokkos community. And yeah, these are some technical details how we could possibly implement this loop unrolling. Yeah, we have to make sure that it works along with this static batch size, which got introduced a little while ago in the case of range policy for CUDA backend. First, we would like to extend static batch size to MDRangePolicy, and also introduce this other way of unrolling, and we could probably call our way of unrolling as unroll factor, and we have to find a way to pass on both these as template parameters. It can be done, no problem. And yeah, we have to look into refactoring device iterate class to do the unrolling along various dimensions. And in order to try these similar ideas for CPU backends, first for loop-based MDRange policy needs to be merged into Kokkos, which is not yet there. We had to look into that. And also, we had to look into test cases for testing ideas about unrolling multiple loops. So whatever I have been presenting so far, it just involves unrolling a single loop. So we need to first look for more benchmark cases where unrolling multiple loops could be useful. And also, when we have this nested for loop-based MDRange policy-based implementation, CPU compilers are pretty good at this unroll and jam transformation, and probably they can readily lead to some performance improvement. And one more small point about improving our benchmark suite. So there is this paper which came last year about just-in-time optimization in Raja. So if you see, they have these two test cases, Edge 3D and the next one. So they achieved considerable improvement in performance purely by loop unrolling, by tuning one loop unrolling threshold, which is used by LLVM, by an LLVM loop unrolling pass inside. So they have, I highlighted that it is exactly only this change that really helped with performance improvement. So yeah, this motivates us to probably expand our performance suite in terms of more application-oriented kernels so that we can try more ideas and develop our tools further. In conclusion, yeah, I just summarized various things I have been talking about. Yeah, we have to look for ideas which are already out there in the loopness optimization community. We have to definitely improve our benchmark suite further in terms of compute-bound and application-oriented code. And ultimately, I think we have to give some more control to the user. And the users are also happy to understand the nuances further and to improve their performance of the code. So in terms of to-do lists, yes, it will be good to implement some of these ideas and try within Kokkos. And as I was saying, it will be good to seek more kernels which can help in studying unrolling along multiple dimensions. Here are some references that could help us with this, with vectorization and loop unrolling. I would like to thank these people for various discussions I have had about this topic. Thank you for your time, and more than questions, we need answers. So please get in touch via Slack with your thoughts. Yeah. Thank you.
All right, we have time for one question while Jakob is getting set up.
Do you have any feeling for how fragile unrolling factors are? What I mean is with respect to switching between different architectures within, different GPUs, even from the same vendor, etc. Like, does the same unroll factor work, or is it, like up and down, and you need to change it for every single architecture you compile for?
It's a good question. Yeah, I think they are quite fragile. I don't have much experience with trying different architectures, but I do notice people tuning both the tile sizes and unrolling in order to get good performance. So it is going to be a little fragile, yes.
Thanks.